All right, this is number 5 from the 2011 Form B AP Physics B exam, and it is an EM problem. We have a radioactive source emitting charged particles, positive Q, into a magnetic field that is also surrounded by an electric field. So we have an electric field with plates above and below, and then a magnetic field out of the page here. And we want to derive an equation for the speed of the particles that move in a straight line through the region. If that particle is moving in a straight line at constant speed and it's a straight line, it means it's in equilibrium. Ultimately, that means the force due to everything needs to cancel out and be equal to 0. So as it's traveling through the field, the positive particle will experience a force upward due to the electric field that wants to go to the negative plate. And if you look at your right hand rules, it also experiences a force due to the magnetic field downward. So for A, the net force is 0, and that comes from the force due to the electric field minus the force due to the magnetic field, which means your electric field needs to equal the magnetic field. We need to come up with this equation ultimately. This is where our goal is to get here. So let's expand the equation for the electric field. That's simply QE, and then the force due to the charged particle is QVB. It's in perfect arrangement, so that's good to go. Now you'll notice the Q's cancel each other out. We can isolate V on its own. V will equal E divided by B. We're going to call it B1 because they call it B1. If you look ahead into the problem, you'll see there's going to be another field introduced in a minute. A2, some of the particles are emitted from the source with speeds greater than this ratio, which the following describes the initial path of these particles immediately after entering the region. Well, if the speed is larger, it's going to affect one of the forces, but not both. The electric force will not be affected. It is only determined from the value of the electric field and the value of the charge itself, which is not changing. However, the magnetic field does depend on the speed of the particle. So if the speed goes up, the magnetic force goes up. And remember, that magnetic force was down. So we're now going to notice a net force downward. However, it still has forward linear speed. Anytime we have a particle with linear speed and a force that's perpendicular to that, you're going to get a curving circular-like path. So it's going to curve, and it's going to curve towards the bottom of the page. And go ahead and explain it the exact same way I just did, that the only one of the two forces that depend on the speed is the magnetic force. Now we're going to add a second magnetic field next to it, B2. Alright, the particle that traveled straight will continue through this region, and then it's going to enter region 2. Notice there is no electric field in the second region. We now want to determine an expression for the initial force the particle experiences here in region 2. However, everything that we answer needs to be in terms of the listed variables and fundamentals. So here's the challenge. We do have only one force acting on it when it's over here, and so the force due to B2 will equal QV times B2. However, from the prior problem, we know that the velocity as it leaves or enters even through this field, that velocity is going to be the E over B1. When it leaves the field, it's going to continue with that same velocity, so that is the velocity in this field. So the force in the second field, and that's what we're looking for, is going to be Q times E times B2 over B1. That should be the final answer. Let's double check that all of our variables are the ones listed or are fundamental. Q is listed, E is listed, B1 and 2 are listed, and F is what we're solving for. So that's all good. C. Describe the changes, if any, in the magnitude and the direction of the magnetic force as the particle moves through region 2. So, as it travels through region 2, mind you, the velocity is constant in terms of its direction, in terms of its magnitude, but not in terms of its direction. So I'm going to just toss this particle already in here somewhere, assuming that it's traveling to the right at that spot, which it really isn't. This is actually right here. I might as well do that. Here's where the particle enters the field with the velocity to the right. its force is going to be downward at that spot. Or no, it's not. The magnetic field is into the page, isn't it? So its force will be upward. That's going to cause this particle to travel in a circular path. However, will it change the actual magnitude of the force? Will the value of that force change as it travels through this field? It won't. So the magnitude stays constant. However, the direction definitely will change. If we draw this particle at a different location, that force is now pointed to the left instead of pointed upward. And it's always going to actually be center seeking as long as the particle is in the field. So you do need to indicate that the magnitude of the force remains constant. However, the direction will change. D, describe the path of the particle in region 2. Well, I've already described this path. At this point in time, we're just going to get it on paper. It's going to travel towards the top of the page in a circular manner. We know it's towards the top because it's got to be opposite of it was in the prior scenario because the field has changed. It's in instead of out of the page. If you use your right-hand rules, you can prove that as well. You're going to have one of your three axes pointed to the right, the other one into the page. That'll leave you with your remaining one pointed up. E, derive the expression for the charge to the mass ratio of the particle, and then we're going to note anything that we didn't already talk about beforehand. So anything that we have been using, we're good to keep using. Well, this is going to be done by looking at the dynamics analysis while it's in the field. While it's in the field, the net force is indeed centripetal. So it's going to be mv squared over r. And that net force comes from the one and only force, qvb, or the magnetic field. Now we already know v is still E over B1. I'm going to reduce this and rearrange this momentarily before I plug this in because I know one of these V's cancels out and we're trying to get to the charge to mass ratio. So I'm going to divide Q over and then cross the V and R over. So I have M over Q will equal R times B divided by M. Sorry, no, R times B divided by V, not M. V is E over B1. I'm dividing, so I'm going to flip that around. This B over here is B2. And how do we want to report R? Is R one of the ones up top? Alright, so this is one that's going to be that was not previously defined, that is going to be in our answer. So we're going to have M over Q will equal R B1 B2 over E1. This isn't actually the final answer because I'm looking at it again. We want the charge to mass ratio. This is the mass to charge ratio, so I got to flip everything up and down. So my final answer, Q over M, will equal E1 divided by R, B1 and B2. Yep, that'll be it. That is the final answer, and that'll be it for number 5. Thank you.